one of my previous videos, I have done the explanation on antenna traps and what they basically do and how do you actually measure them. And I've used one of the 5 different ways that I do know how to measure the actual traps, and that was by using a spectrum analyzer and a sweep generator. And so I'm not going to go into the explanations, what is the antenna trap and what does it do and things like that, because I have already done that. And on this pamphlet, basically, just to repeat anyway, for the sake of the guys that they haven't seen the previous video number 1, the antenna trap blocks a certain frequency. This shields part of the antenna for higher frequencies where a shorter antenna is needed. The antenna, the entire, should I say, antenna participates for the lower frequencies on which the trap does not block. This can be applied in dipole antennas where each leg of the antenna needs a trap, but also in end-fed and vertical antennas where only one trap is needed. So in actual fact, the trap, this is the trap. Now there's basically 2 different types of traps. One is made out of copper wire, windings of copper wire, in other words, a coil of a specific inductance and the capacitor of a specific capacitance. And then, of course, then you get, and that would look something like this, very small, physically small, which already got it stuck on the instrument. And then the second one would be made out of coaxial cable. And this specific one I have, that I'm going to do the demo, is 40 meter. Which is 7 to 7.2 megahertz. It's a 40 meter band, which allows radio amateur to transmit 26 dBW or 400 watt power into the actual antenna. So now, basically, okay, I'm going to show you today a different way of measuring also accurately by using my MFJ instrument, antenna analyzer or impedance analyzer, should I say. So I already got the setup over here. I got my little loop that I made, specific loop that I connected up into the instrument, and my trap is actually right in the center, if you can actually see it. Okay, I've used the peg in order, for metal to be away from the from the actual loop and things like that. So now let's go and try and measure it and see how accurate and how good we can actually get it. And I'm going to show you one thing. You will be amazed how accurate actually it is. Okay, now I'm just going to try to increase the... Okay, now let me just enable the instrument. Now, I do know it's for approximately 7 megahertz. So I'm going to start, say, from 5 megahertz sweeping. 2 things one must watch out for and look, where the resonant frequency of the trap is. And that would be the SWR and the XLR, which is a reactive component of the actual trap. So the smallest dip here and the smallest over here, that would be the resonant frequency of this particular trap. And the trap always should be tuned slightly below the actual resonant frequency of the frequency that you want to use it for. The reason why, so you don't get the high losses incurring within the trap. All right, on that note, let's start. Okay, so I'm going to actually sweep. And if you see over here, let me try and zoom a little bit more if I can. Okay, now let's do this. All right. So now, okay, it's a bit too much. Okay, let me zoom out of it. Okay, let's leave it over there. Okay, now if I keep on increasing the actual frequency, you can see we watch over here to get the lowest reading. And of course, our reactive resistance must be the smallest. So we are already on 6,6, approaching 7 megahertz. 3,6, 3,5, you can see the SW is going down, so is the resistance. And then if you look at it over here, 6,955, okay, now if I just go over, can you see now I'm going up in SWR. So I go slightly back, 2,9, looks like that's where it would be, the resonant frequency. So the resonant frequency of this particular trap, that I'm actually using it for the demo traps that we make, is perfectly tuned for a basically 7 to 7,2 megahertz application. Now I'm going to try, okay, that is the capacitor and the copper wire, the actual coil that makes the resonant frequency. So I basically demonstrated the trap that we make made out of coil and a capacitor. Now I'm going to show you how accurate it is with basically a coaxial cable. All right, now what I'm going to do, let me just zoom out. Okay, I'm just going to disconnect this here. Okay, and I'm going to remove this. And I'm going to try to fit a bigger loop, okay, because it's a much bigger and it's used specifically for coaxial cables, because coaxial cables, they have got a bigger Q than the actual coil and a capacitor, the bigger Q factor, should I say. Okay, so let's see now, let's put it again. And we put it in the center. Let's do it this way. More or less there. Okay. Let's see what happens. All right. Okay, wait, let me just try to. It's quite difficult because it's quite heavy. Okay, now let's try and do it. All right. Now, let's try and do it. So if I carry on now, you can see we're still looking for the lowest dip. Okay, where is it now? 6,9. Okay, let me do it this way. Let me stop it. Okay, right now we're gonna do the coaxial trap measurement with the MFJ. Just now we did a measurement of the coil with the capacitor. Coil and a capacitor, yes, they've got advantage and disadvantages. So you can't say one is better than the other. This one has got a much lower Q factor than the actual coaxial cable. So the impedance would be a much greater with and much sharper point with the coaxial, which you will see just now. Okay, I'm still using my MFJ. And basically I have got my special little loop that I have made for the coaxial cable type of thing, okay, which is connected into the MFJ. Now let's go and measure it and see what is actually happening. Of course, let me try to increase here so you can see it a bit better. Let's just do it this way. Okay. And that's fine. Okay, again, we're starting from about 5, something megahertz, wherever, okay, from a lower frequency. And we know it's a 40, we know that this strap is for 40 meter, which is 7 to 7,2. So let's start, say, from 5 something, as you can see it over there, 5,7 megahertz. Okay, let me just focus it properly. All right, it is in focus. Now I'm going to start sweeping. Again, we need the smallest SWR, and of course the XL must be as small as possible. Okay, if we actually go, but specifically SWR, that is the main thing that we must look for. Now I'm keep on sweeping. You can see we reached the 6 megahertz, 6,1, 6,2, 6,5. Okay, 6,7. You can see, aha, it's going down. Okay, You can see when this is going down 2,3, we go of course to the lowest point, 1,2, 1,1. Let's see if we can go to 1,0. Okay. All right. Now, more or less, you can see the XL is 0, and most importantly, SWR is actually 1.1, and that is the lowest point. So the resonant frequency is at 7,057 megahertz, which is perfect for 40 meter band for this particular trap. So this trap made by us, you can see how accurately it's actually pre-tuned and scientifically sort of tuned and sort of assembled for the accuracy. So basically what we have done right now, we have demonstrated, okay, let me just zoom out, 2 different traps. One with a capacitor and a coil, okay, and then of course another one which is, and this particular one, let me just disconnect it, which is this one here, which is made out of coaxial cable. And yeah, on that note, basically I quickly demonstrated how to test basically traps with a MFJ, with the MFJ analyzer. In a part 3, probably I will use the sort of different method, a third method. So you can see these various ways, as they say, to skin the cat. And so is also in measurement of the resonant frequency of the actual traps, whether it's a coaxial or whether it's a capacitor and a inductor in parallel. On that note, thank you for watching, and I hope you enjoyed the Batos MFJ antenna trap measurements, how to measure. Thank you.